The last type of hydrocarbon we are going to take a look at are aromatic compounds. So remember at the beginning of these lessons, we talked about how there's different categories of hydrocarbon compounds. One of those was aliphatics, which is where we look at alkenes, alkanes, alkynes, and the cyclo molecules with that. And then the other category of hydrocarbons is aromatics. That's what we're taking a look at today. So you can see where aromatics are found in biological compounds as well as man-made or synthetic compounds, and so why those might be important in the world. In order to be an aromatic compound, the compound must contain what's called a benzene ring. Okay? Benzene has the molecular formula of C6H6. And if you want to challenge yourself, then pause the video here and see if you can figure out a way to put together 6 carbons and 6 hydrogens. So there we go. Here we have what a benzene ring looks like. So it looks like a cyclohexane molecule, except for it has 3 double bonds in it. Now, what's actually special about benzene, so for example, I'm just going to number this ring, 1, 2, 3, 4, 5, and 6, and we would never number a benzene ring, and I'll hopefully make it clear why that would happen. Now what happens with benzene is actually this double bond here, so remember that every bond is a pair of electrons, so this double bond here, or the second one in it, sometimes says, meh, I don't know if I want to hang out between carbons 1 and 2. I'm going to shift over here. But then if you take a look at what happens when that happens, this carbon, which I've labeled number 3, and again these numbers are just for ease of reference, okay, not for any actual purposes. This carbon is then going to be bonded to 1, this single bond that was here. Now we've moved another pair of electrons, so that's a double bond. And then a double bond between the 3rd and 4th carbon, and this single bond coming up for hydrogen. Well, that's 5 things. So carbon number 3 is going to say, ooh, actually, if this double bond could just move down here, that would be great. Carbon 5 then says, well, I'm actually going to move this double bond here between 6 and 1. Okay, so what happens is we see what's called a resonance structure, and that's just nice to know, not need to know for this particular course. So we see a resonance structure, and I'm going to draw and number these carbons the same way, just so, again, the numbers don't mean anything, but just so you guys have a little bit of ease of reference here. Where do we start? 1, 2, 3, 4, 5, and 6. Okay? So sometimes in benzene, and I'm talking the same molecule here, so sometimes in the same benzene molecule, we've got double bonds between 1 and 2, 3 and 4, and 5 and 6. And then when those electrons decide they want to travel and see more of the carbon ring, they'll shift to be between 2 and 3, 4 and 5, and 6 and 1. Now because what happens is, well then perhaps these electrons decide to move to be back between 1 and 2 again. So this is, the benzene molecule is constantly going back and forth between these two different resonance structures. So what we tend to see as a drawing for benzene is something that looks like this. That should be connected there. And this is where organic chem is really going to pay off. You guys should all be great at drawing hexagons by the time you are done with this lesson. We draw the circle in the middle here to show the resonance, to show that sometimes double bonds are, you know, at 1, 3, and 5, and sometimes they're at 2, 4, and 6. The compound is constantly moving back and forth between where the double bonds are located. Okay. Line diagrams are also more commonly used for benzene rings, as I've drawn here in the red, than a structural or condensed structural formula. So what you need to remember is that each of these carbons here is bonded to one hydrogen. It's single bonded to a carbon, double bonded to the one next to it. So it has all four bonds that carbon must be bonded to, already spoken for, I guess. Okay. Let's take a look then at what's exciting about aromatics. They are very stable compounds. They have low reactivity, and they are unsaturated. We know that they're unsaturated because they have those double bonds present. Anytime there's a double or triple bond present, that's an unsaturated compound that we're dealing with. However, benzene is a little bit funny. It behaves and reacts more like a saturated compound. So if you go on to take a look at different types of reactions that organic compounds can have, you'll see benzene and aromatic compounds tend to react more similarly to alkanes, so saturated compounds, than they do to alkenes or alkynes. Rules for naming aromatics. Benzene is usually the parent chain, and we're going to go through an example when it is, as well as several examples of when it is not. So I'll give you the three different situations of when benzene is not the parent chain, but it's usually the parent chain. Again, we want to give the branches the lowest possible numbers, similarly to how we did with cycloalkanes and alkenes and alkynes, all cyclo compounds there. We are going to make sure that those numbers add up to be the lowest possible sum. So numbers of branches add to be the lowest possible sum. And then when you put the whole name together, remember commas to separate numbers from numbers, dashes to separate numbers from words, and then the last part of the name is written as all one word. Now, one thing I do have to point out to you, when benzene is a branch, and again, I'm going to show you three situations where it would be a branch and not the parent chain, we call it phenyl. P-H-E-N-Y-L. So why we don't call it benzyl, I'll never know. But we call it a phenyl branch. So let's take a look at some examples then. Our first one here, we do have benzene as our parent chain. So when we number, we want to make sure that we give the branches the lowest possible number. So obviously one of these branches, guys, has to be number 1. And again, just like with cyclo compounds, you can number clockwise or counterclockwise. I'm going to start here. And if you're ever not sure of yourself, then remember that you can add up the sum of the numbers of the locations of all the branches. You want that sum to be as low as possible. So here I've got my parent, which I've identified as benzene. And for my branches, 3 methyl branches at locations 1, 2, and 4. Because there's 3, I'll use that prefix tri. And then when I put this whole name together, okay, I want to make sure that I have my correct punctuation and that I'm spelling everything as all one word. 1, 2, 4, trimethyl benzene. Pretty straightforward. I don't anticipate a lot of difficulty naming aromatic compounds where benzene is the parent. So let's take a look at, well, what's a little bit more challenging, and that is when benzene is not the parent. So as I told you, there's 3 situations where benzene is not going to be the parent. This is not one of them. Oops, my bad. Let's take a look at another example. I know why this one's in here. So I wanted to show you the importance of naming or numbering rather, and what the rules are for that. So you can see clearly I've got 3 branches. Now, I'm either going to be able to start at this branch here and number clockwise, or I'm going to be able to start at this branch here and number counterclockwise. You can see that regardless of what I do, I'm going to get branches at numbers 1, 2, and 3. So what do I do with this? Well, the rule, guys, first, please, let's be clear. Keep in mind the first rule, which is to give branches the lowest possible numbers. That's rule 1. When I can still do that and I'll get the same results regardless of kind of where I start or what direction I go in, what I want to do is give alphabetical preference. So this branch here is an ethyl group. These other 2 branches are methyl groups. I am going to give alphabetical preference to that one. Call it number 1 and number those other 2 accordingly. Okay? So my parent here, as I said, is benzene. And then branches, I've got an ethyl branch off the first carbon. And even though it's off the first carbon, I still need to list it. And 2 methyl branches off the second and third carbons in my benzene ring. Now, when I put this together, remember I want to alphabetize, but I alphabetize only according to the name of the branch, not this prefix. So the name of the branches off 2 and 3 is methyl, so that's where I start my alphabetization. Again, it's just one of those things that perhaps it doesn't make the most sense, and perhaps it's just people being super picky in the naming. That's how it is, though. Okay? So when I put this name together, 1 ethyl, 2, 3 dimethyl, benzene. There we go. So now let's take a look at examples where benzene is not the parent chain. So the question, when is benzene not the parent chain? Sounds like the start of a really cheesy joke. I'm not going to make this one, though. There's far too many other cheesy jokes to be made in organic chemistry. Come ask me and I'll tell you some. When is benzene not the parent chain? Well, the first case is when what looks like a branch is longer than 6 carbons. So right now, just looking at this molecule, it looks like this giant mess of a line diagram is our branch. Looks like it. Okay. However, if you start counting the number of carbons in there, we're going to have 1, 2, 3, 4, 5, 6, 7, and 8 carbons. Okay, well that is clearly more than 6. 8 is more than 6. Okay, so in this particular case, our branch is actually the benzene ring. All right. So just so you can make sure that you jot this down, when is benzene not the parent chain? Case number 1, when the branch, in quotation marks, or what looks like the branch, is longer than 6 carbons. How are we going to name this? Well, I've actually gotten a really good start. I've found my parent chain. Okay, I've also numbered it. It's got 8 carbons, so that's octane. And then, well, what's my branch? This guy right here. Okay, off the first carbon, we have a benzene ring as a branch. What do we call that again? It's not benzene. Phenyl. Okay, so name of this guy, 1 phenyl octane. 1 phenyl octane. Next example. When is benzene not the parent chain? Second occasion. So I'm just going to circle what you may look or you might think is the branch. Okay, and that is this little line diagram coming off the left-hand side here. Okay, looks like a branch, and then this branch, again in quotation marks, is branched. What did I just say? Okay, so here is how this is happening. I'll erase this after so we can start with a fresh diagram. Okay, we have this little line coming out. Well, actually, you could continue it on there. Okay, that could be a chain. But then also off, and by chain I mean it looks like a branch. And if it was just that part, it would be a branch. Okay. However, then we start going in this other direction here too, and we get a new chain. Okay, so in this course, you don't know how to name this particular branch, that's in quotation marks. This mess here is going to be your parent chain. Okay, also, if we take a look and we number it, we can see that we've got 1, 2, 3, 4, 5, 6, 7, 8 carbons in that parent chain. So again, it goes back to our first scenario where our parent chain is actually longer than 6 carbons. So what's the parent in this case? Again, I just numbered it, and it's going to be octane. What's my branch? Well, same as last time, it's going to be a phenyl. This time it's off carbon number 4. And then putting the whole name together. For phenyl octane. When is benzene not the parent chain? Second scenario, when the branch, in quotation marks, looks branched. That means it's actually the parent chain itself. Okay? Last one. Case 3. When is benzene not the parent chain? When you have either a cyclo compound or something, an alkene or an alkyne in what looks like the branch. That's not a branch. That's going to be your parent chain. So you guys wouldn't necessarily know how to name this particular branch that I've circled here as a branch. That's because it's going to be our parent chain. So what is our parent chain? That is 6-sided, right? So that needs to be, and it's a cyclical molecule, no double bonds, so cyclohexane. Okay, and if we number our friendly cyclohexane, well, either way you want to go after that, we can see that we've got a couple of branches off the first carbon. Okay, so we've got a methyl branch and our friend benzene ring, which we call a phenyl branch. Putting this together, remembering to alphabetize one methyl, one phenyl, cyclohexane. So the key with aromatics is going to be just to simply recognize when is benzene the parent chain, when is it actually a branch, which we call phenyl. The more examples and practice that you're able to get in, the easier time you will have identifying these things on a test or quiz or lab or anything like that. Good luck!